Hello everyone and welcome back to the CS184 discussion recordings. Today we have a very short discussion on color, so we'll go through that and then we'll go ahead and do a practice problem from the spring 2018 midterm in preparation for the midterm next week. Okay, so let's get started with the color portion of the discussion. So before we get started, I'm just going to do a very short intro into color. Just in case you didn't get a chance to look at the lecture or the slides. So let's get started. Okay, so the basic idea behind colors is that there are three types of cones in everyone's eyes. Okay, three types of cones. There's the S, M, and the L. Okay, and the way these cones work is there's essentially a graph that looks something like this. And on one side you have wavelength, and on one side you have response. Sorry, I messed that up. And what you get basically is three different curves that look something like this. Okay, for S, M, and L. So essentially, each of these cones responds differently to different wavelengths of light, right? S has a higher response to lower wavelengths, M is kind of medium, and then L has a response to the largest wavelengths. And then so together, you end up getting the responses of all three of these, and you can kind of calculate that, right, using something like this. So the response from S is going to be this integral over, so Rs of lambda, and this is the kind of the response function of S, times S of lambda, which is, how much of that wavelength is actually there, d lambda. And then, the same thing for M, and the same thing for L, except, RL, RM, so on and so forth, right? So this is the response, and this is the wavelength, and when you integrate together over the entire spectrum of wavelengths, you get the total response from the S, M, and L cones, okay? And these responses are basically how your brain decides what color you're seeing and, how your eyes work, okay? And so one of the common things that we do is we represent this as a matrix vector multiplication, okay? And so to do that, I'm going to go ahead and erase this integral formulation. And so what it's going to become is it's going to become a vector here with the S, M, and L responses. And that's going to be equal to a matrix, right, with R of S, R of M, and R of L. So these are the response functions, right? So one for every wavelength, right? We might have that many numbers, and each of them has a number which tells you how does this cell cone type respond to this wavelength. And then what you're going to do is you're going to multiply by a vector S, which is basically going to tell us how much of each wavelength is present in the light we're seeing. And so when you do this matrix vector multiplication, it's essentially the same as the integral, right? The R of S times S, sum it all up, just like the integral does, and you get S, same with M, and same with L. Okay, so once again, this is the spectrum, and these are the responses. And you multiply it together, and you get the total activations. Okay, so that's kind of the basics of color. For more detail, definitely look through the I'm blanking right now. Sorry, look through the lecture slides and watch the lecture. There'll be much more detail there that should hopefully make this clear if I sped over it a little bit. Okay, so let's keep going. Let's look at some of these questions and see what we can do. So first of all, the first question is, what is a metamer and why are metamers useful? Okay, so what a metamer is basically two different spectrum that result in the same response. Essentially, it's two different values of this S right here that give you the same S, M, and L outputs on the left side. Okay, and so let me write this down. So a metamer are different spectrum with the same response. Okay, so they're different metamer with the same response, so different, different amounts of light, but you get the same thing out. And they're useful because what this allows us to do is, our screens are often limited in the range of spectra that they can show. They're limited by the pixels, by the technology, and all of that. But what metamers allow us to do is basically we can mimic other colors that we may not normally be able to show. We can reproduce them with other spectra that we can actually show. Okay, so allows us to reproduce hard spectra on screens. Okay, so metamers are a useful tool. They basically allow our screens to display some colors that they normally couldn't or couldn't otherwise, because basically, it can double up. Okay, so let's keep going. So what are some common problems associated with defining a color space? Okay, so a color space is basically kind of the range of colors that something can show. A display, a screen, TV, whatever it is, right? So what are some of the common problems with this? And so one of the biggest problems is that it's device dependent, right? Different devices have different tech in them, and so that affects the range of colors they can show, how bright these colors can be, how many different colors they can show, all of that stuff. So it's awfully device dependent, and so it's not easy to create, one color space that's uniform for a lot of different things. And so the second is, and this kind of falls under, we kind of briefly talked about this, and that's limited gamut. And so what the gamut is the range of colors. Range of colors. Right? So different screens will have different range of colors that they can possibly display. And so that's going to be one of the considerations that we have to take in mind when we're defining a color space, because we have to know, what range of colors can we actually display, and make sure that our color space kind of follows along with that. Okay, so those are some of the common problems associated with defining a color space, and let's keep going. Okay, so what is the purpose of the CIE chromaticity diagram, and how is it read? Okay, why is black not on this diagram? So if you don't know what this diagram looks like, I would highly suggest that you go to the lecture slides, or just, go online, look up I think it's CIE lab color space. So CIE and then a lab afterwards, look up the color space and look what that, just look it up, basically check it out, see what it's all about. But what we're going to do is we're going to discuss it real quick. Okay, so the purpose of this diagram and how it's read is, okay, give me 1 second. Okay, so basically what this diagram is it's purely a chromaticity diagram, okay? This word right there is the key. So, and the way this diagram works is basically the chromaticity is the quality of a color, okay? So quality is I know it's tricky, but it basically means kind of like the underlying actual color that it is, okay? And so the reason this is, different from anything else is that it doesn't take into account luminance or brightness, okay? So it's really just focused on what the color is rather than how bright this color is, okay? So it's, let me write this down, purely chromaticity, no luminance, whoops, no luminance. Okay, so that's what it is, right? It's purely chromaticity. It's the quality of a color, doesn't matter, how bright it is or anything. And so that's kind of the main purpose of this CIE diagram, right? There's no luminance involved, whereas a lot of other color diagrams will have that. And because of this characteristic, because there's no, concept of this luminance or brightness, that's why there's no black. No black. Okay, and so, okay, I guess I forgot to really quickly mention how to read this diagram. So let me just kind of give myself some space. And so the way to read this diagram is the pure colors on the edges. Okay, so if you look at this diagram up, it looks kind of like almost like a horseshoe type diagram, right? And so the very pure colors are on the edges of this horseshoe. Here, let me draw. It looks something like that, basically. And the pure colors are all along the edges. And then as you go inwards, basically what you're going to get is that the colors become more and more desaturated, okay? So, oftentimes some of you may have heard the concepts of hue and saturation. So that's basically, those are the two things that vary on this CIE diagram. So the hue varies around the edge, right, over here, and then the saturation varies as you go in to the center of the diagram. Okay, so let me get rid of this diagram. Once again, I would say definitely look it up. Look this diagram up, read it in a little more detail. It'll be good. It's good to know. You won't really need to know exactly, too many details about this diagram for this class, but it's still good to kind of just take a look at it and get an idea of what it is. Okay, so pure colors on the edges, and then desaturate as you move in. Okay, so that is the CIE chromaticity diagram and how it's read. Okay, so last question of this discussion, real quick. What is the goal of the CIE lab color space? So, this is a slightly different name, CIE lab, but it's the same thing as this. It's a color space, right? And so, what's the goal? And the goal of this is perceptual uniformity across colors. Okay, and so the main idea there is that, there isn't a lot of variation in the brightness or anything like that across colors. The different colors look very much the same. Obviously they're different colors, but some don't look brighter or darker or anything like that. There's a sort of uniformity across all colors. Okay, and that's the main point of the CIE lab color space. And so the reason the LAB is actually there, right? There's the CIE and then the lab, and so each of those letters, L, A, and B, stands for something. So L stands for lightness. A stands for the red-green amount. And B stands for the blue-yellow amount. Okay, and this isn't super important to know. It's just kind of extra knowledge, good to know. But once again, I would highly suggest you look up the CIE diagram, look up the CIE lab color space, look all that up. It'll be basically just good learning for this class, good background information that should be useful. Okay, and yeah, so perceptual uniformity across all colors. So CIE lab is often used in, it's sort of a device independent way. Up here we talked about how one of the common problems with this associated with defining a color space is that the color space is device dependent. It looks different on different devices. Different devices have different range, so some colors may not be in there, all of that. But the goal of the CIE lab color space is that it's device independent, so the colors are defined independently of how devices use them, and that's the goal. Okay, perceptual uniformity across colors. Okay, so that's all for this discussion. It's a really short one. Color is it's a good topic, an important topic. I'd suggest look at the slides for more details, specifically about the cones, and this matrix formulation, linear algebra formulation. And this formulation will be useful for the tests, so definitely check that out. Okay, so now that we've done that, what we're going to do is transition a little bit and work on a practice problem from the Spring 2018 Midterm 1. Okay, so if you want to do this on your own, you don't want to see the solution yet, definitely take a stab at it. I'm going to go through it, so if you want to come back later and look at the solutions, that's totally fine. Okay, so let's get started. So suppose we are trying to calculate the diffuse Lambertian term of the shaded color for a surface point P0 as shown below. Okay, so it's right there. In world coordinates, let P0 be 3, 4, 3, and let it be the origin of the object's coordinate system. Okay, so the object is this blue slab, and let the object's local axes be x is 0, 0, 1, y is 0, 1, 0, and z is negative 1, 0, 0. Okay, and the scene has a single point light located at PL is equal to 1, 6, 3, also in world coordinates. Okay, so that's right there. Up and to the left, we got P0, X0, Y0, and Z0. And so, okay, these are all in world coordinates, but P0 is the origin of the object's coordinate system. Okay, and the axes are in the object coordinate system. So, first question. What is the homogeneous change of coordinates matrix from object to world space? Okay, and then, so what is the matrix M O2W such that M of O2W times x in object space is equal to x in the world space, right? And so they give us a little hint of the form, just basic, homogeneous coordinates, right? Okay, so let's set this up. This is it may look a little complicated, but it's actually a relatively simple question. So let's set it up, right? They gave us the hint. Let's use it. So the bottom row is 0, 0, 0, 1. Okay, so first of all, let's look at this. The rightmost column is the translation, right? In a homogeneous matrix, the rightmost is the translation. So we want to see what's the translation between the origin of the origin of the object and origin of the world, right? So how do we go from one to the other, basically? And so the answer to that is we're going to go 3, 4, 3, right? Because 3, 4, 3 is the origin of the object's coordinate system, and 0, 0, 0 is the world coordinate system, right? So basically the point is if we start in the object's coordinate system and we have 0, 0, 0, right? So the origin in the object's coordinate system, and we want to translate this into world, what we expect to get back is 3, 4, 3, right? So if we just ignore the first three columns because it's 0, 0, 0, right? Then all that matters is this translation, and that's going to be, okay, and that's going to be 3, 4, 3, okay? So now let's keep going and let's set up the rest of the columns. So First of all, now let's look at the x column, right? So this is also quite simple, and if you remember back to when we were looking at transformations, what you want each of these to be is what each axis is transformed into in this new space, right? So basically what this is going to be is we're going to put the x axis here, right? So 1, 0, 1 is going to become 0, 0, 1. And then for y, similarly, we go 0, 1, 0. And then for z, we go negative 1, 0, 0. Okay, and that's it. There we go. We have our transformation matrix MO2W. Okay, so let's keep going. So next, number 2, the diffuse Lambertian term of surface shading calculation has this form, right? LD is equal to KD times I over R squared, max of O n dot L. And for this light, KD is equal to 1 and I is equal to 16. What is R squared for the given point on the surface with respect to the light? Okay, so this is pretty simple, just, some straight up math. So we're going to go R squared is equal to, it's going to be 163, the position of the light, minus 343, the position of the point, right? And then all squared. Or, well, I guess that's a kind of bad way to do it, but the radius squared, and so what that's going to be is it's going to become 2, or negative 2, 2, 0, right? And if we take the length of this, it's going to become 4 plus 4 is equal to 8. Okay, so R squared is equal to 8. Just some, vector math. Okay, so next, what is L in object coordinates normalized? Okay, so we have up here, we found object to world. Now we want world to object, right? And so the way we're going to do that is take the inverse. And I'm not going to take the inverse here because, it's a 4x4 matrix. That would take me quite a while. But I'm going to go ahead and just give you all the answer. Okay, so let me write down the answer. Okay, there we go. So that's the world to object transformation. And then we're going to want to find the difference, right? So what we're going to want to find is the position in relative to the origin, right? We want to find this object coordinates. So look, the origin in this case is 3, 4, 3, right? That's the... Oh, I'm sorry. Okay, so 3, 4, 3 is the origin of the object's coordinate system, and PL is 1, 6, 3. So what we're going to do is, once again, we're going to do PL minus P0, and we're going to get the same answer we did above, 2, negative 2, 0, right? And then what we're going to do is multiply. So we're going to take this is in world coordinates, and we're going to multiply it by this matrix, right? And so what we're going to get is L is equal to M W20 times D. And once again, I'm just going to give you the answer, but do check it out on your own. And it's going to look like that. Okay? So there we go. We have our L. And then now we just normalize all of this, and L norm is going to be equal to 0, root 2 over 2, root 2 over 2, and 0. Okay, so we did some math, got the inverse, subtracted, multiplied, and we got our answer. Okay, so last question now, putting it all together, what's the diffuse term? And so we're basically just plugging into this equation. So L of D, so KD is equal to 1, right? So it's going to be L of D is equal to 1 times I is 16, 16 over 8 squared, so 64, right? And, oh, sorry, that's my bad, actually. 8 is already R squared, so that's 8. And then the max of 0, comma, n dot L. Okay, and so then we're going to go, it's 2 times root 2 over 2, right? Because we can come over here and find the normal. And so we're going to get that, root 2 over 2. And so if we multiply this out, these cancel, and it's root 2. So LD. Okay, so there we go. That's one practice problem from the Spring 18 test and some color questions. And that's all for this discussion.